Alright, in this section here, we are still talking about optimization problems. Alright, we've got a farmer who's got 400 feet of fencing to enclose two adjacent corrals, and he wants to find the dimensions or the dimension of the corral so that the area inside is a maximum. So this is kind of a typical optimization problem that you'll find in an engineering calculus class or in just a survey calculus class. Alright, well, let's get started. First thing I'm going to do here is draw us a picture of this corral, and I don't know, we'll just use red. How's that? So it doesn't look like, oh my god, things aren't very straight here. Okay. So we got two adjacent corrals, and let's go ahead and label their dimensions. So this is the width, and width. So, you know, I know this picture's not very good, but anyway, this distance from here to here, right, straight across is all equal. These guys are all equal. And this is the length, right, straight across, and same thing here. All right, so not a very good picture, but at least you get the idea. So we want to find what the dimensions are. We want to find W and L. So these are going to be our two unknowns, right, is WL, and they gave us some additional information, and that is that the farmer has 400 feet of fencing. So we want to maximize the area, so I'm going to write it out like this right here. A is area. We want to maximize the area, and the perimeter we're given 400 feet. So we need to construct these two equations now. This one up here, this is our area that's to be maximized, and we can simply write this as A is equal to, and we can say W times L. How's that? So W times L, and then the parameter, I'm going to go ahead and just write it over here. So P is equal to, now the perimeter, right, that's going to be right, all of this fencing right here, okay, and so we got 3W plus 2L. So there we go. We've set up our two equations here, and what we're going to want to do now is go ahead and plug in our 200 for our P, or not 200, 400. 400 is equal to 3W plus 2L. And of course, this is what we are going to be maximizing. I'm not going to rewrite that again. But what we're going to want to do now is get this thing all in terms of, or get this in terms of one of the variables, W or L. And I don't know, it doesn't really matter. I'm going to just go ahead and just solve for L in this problem, I guess. So 400 minus 3W is equal to 2L, and then what we're going to do is multiply. We're going to multiply through by a half all the way across, so this becomes 200 minus 3 over 2W is equal to L. There we go. So we got L in terms of things are going to be, it looks like up here in terms of W, right? So I'm going to now go ahead and write this guy out. Area is equal to, so we're substituting this W in, or I'm sorry, this L in right here. So let me just rewrite the W. L is equal to all of this stuff here, and this is going to be 200 minus 3 halves W, right? And we want to put a parentheses around that. Okay, let's put a parentheses around that, and we can go ahead and graph this, right? Remember, we can graph this and then take a look at where we're trying to maximize, right? Where the on the graph where that would occur. But we're going to go ahead and do the calculus. What I'm going to do here is distribute this W across. So we have 200 W minus 3 halves W squared. So now let's do the calculus, taking the derivative. I'm going to say a prime is equal to, so this becomes 200 minus, right, take the 2 out front, so we have 3/2 times 2 is just 3w. And now of course we want to set this equal to 0, and solve for w. So it looks like we have 3w is equal to 200. Alright, and then we just multiply both sides by 1/3, so we end up with w is equal to 200 over 3. So this is going to be our width, and of course you can go ahead and approximate that if you'd like. And now to find L, we got to remember what our relationship was with L, right? And that would be right up here. We had 200 minus 3/2 w. 200 minus 3/2 w, so you remember that. 200 minus 3/2 w, that's our relationship. And now we're going to go ahead and find out what that L actually is by taking our w here, which is 200 over 3. And now we're going to do some basic math. L is equal to 200, and of course those guys cancel out. 2 goes into 200, right? So that's going to be left with a 100. So minus 100, and therefore L is equal to 100. So remember our units is feet, right? Don't want to forget our units. And of course, we'll need to plug that into a calculator and approximate that. So we have our dimensions. Let's go back up to the top. Okay, so the dimensions here, this was 200 over 3, and L going in this direction is going to be, we said 100 feet. Of course, let's not leave off our units here, right? And anyway, this is equal to, I think I was 66.7. I think I rounded it there, but anyway, 66.7 feet. So at least that gives us an idea, right, of what our W is. So we took our given information that they gave us, we constructed our primary and our secondary equations somewhere right here. The primary equation, the secondary, I guess I should underline this right here, our secondary equation, got everything in terms of one of the variables, wrote it out, took the derivative, set it equal to 0, solved for it, then took it and plugged it back in to, once we solved for one of our variables, went back to our secondary equation, plugged it in to find out what the other variable is. So that's basically the format that you use on all of these optimization problems. And sorry things are a little sloppy here. I'll try to improve that. Right, I'm writing on a tablet. It's got a real slick surface, and so it a handheld tab, not a computer tablet, but a writing tablet. Anyway, guess enough excuses on that. But okay, well, I'm going to move on and make some more of these tutorials. Alright, we are working optimization problems. Alright, so these, like I said earlier in some previous problems that we worked, these problems are going to get just a little bit more difficult. In this particular one, we're going to be finding the maximum volume of a rectangular solid that has a square bottom and a surface area of 200 meters squared. Now, actually what we're going to be doing is just finding the dimensions We're not going to actually find the volume, but we want to maximize the volume. But we're just going to find the dimensions of this rectangular solid. So let's get started. Alright, so I guess there's a couple things that I need to do before we actually start doing any math. The first thing I'm going to do is I'm going to draw us a rectangular solid over here so we get an idea of what we're talking about. Anyway, I'll attempt to draw it anyhow. Okay. And so it's going to look something similar to this. So this way you get an idea of what it is we're talking about. Now, this thing has a square base, and that means that this side will be x, this distance, and this distance here is going to be x also, right? That distance, and then this distance is x. And then, of course, this distance, the height of it, how about we just call h, okay? So this would be the height of the solid. Alright, we got that out of the way. Okay, so let's remind ourselves what we're doing here. We'll let V be the volume here, and we want to find the maximum volume. Alright, and one of our constraints is we only have, I believe it was 200 meters squared of surface area. So our surface area, which I'll just call S, is 200 square meters or something like that. Okay. Alright, so we're going to write the equation or the formula, however you want to say it, to find the volume. So the volume is equal to, now we have x times h, right? That would be the volume. So that volume ends up being x squared, let's say, times h. And then now we've got the surface area. So the surface area, like for example, one side of this is going to be h times x, right? So that would be the area of this side right here. And of course we have how many sides to this thing? We're going to have this side, and then the back side, and then the other left side over here. So that's h times x, and that you got 1, 2, 3, 4 sides to that. And I'm going to go ahead and just write s here for the surface area. So we're going to have we are going to have 4 of those, so 4 h times x's plus, and then of course we have this surface area on top and then the surface area down here on bottom. And so this area here, remember, is x times x, that's x squared, and then you have x times x, and that's another x squared, so you end up having 2 of those guys, right? So we've had to kind of construct our primary equation and our secondary equation. So now from here we are going to let the surface area, remember, is 200 equal to 4hx plus 2x squared. So we're going to want to get our primary equation here all in terms of one variable, and we're going to do that by getting it in terms of x. So we need to solve for h down here in this problem. Right, we're going to want to solve for h, and that's easy enough to do. And okay, we got 200 minus 2x squared, and we're going to be left with the 4hx over here on the right hand side. Now of course what I want to do is I got to isolate this h. I'm going to divide or multiply both sides by 1 over 4x. Rewriting. and we have 4x is now equal to h. Great. We can split this up if you want, but I think what I'm going to do is go ahead and keep this just like it is, and now I'm going to go up and do that substitution. But I think I'll just rewrite it here instead of scrolling back up the screen. So remember, this was x squared times h. Now we're going to take all of this piece right here and plug it right on in, substitute it in for this h. So we have v is equal to x squared times, now I'm going to put a parentheses here around 200 minus 2x squared over 4x. We can cancel some things out here. So we have an x down here in the denominator, and we have two x's up here in the numerator, so we can cancel out one of these x's. This is the intermediate steps that usually slow people down in calculus. And of course, we still have 4 down here in the bottom. But we're going to go ahead and split that up also, and I'm going to distribute this x across. So we have v is equal to, so 4 right goes into 200, and we should be left with a 50, and then I'm going to distribute this x across at the same time. So we're going to be left with a 50x, and then distributing the x across again, but the 2 goes into the 4 twice, and we're going to be left with an x cubed over 2. Now we can finally take the derivative. So v prime is equal to 50 minus 3x squared over 2. We want to set this equal to 0 and solve for x. I'm going to take the 3 halves x squared over to the left, and really the real reason for all that is because we have a minus sign out front. And then we can multiply this both sides by 2/3, multiplying both sides by 2/3, and we're left with x squared is equal to 100 over 3. Now you're going to want to square root both sides. I'm going to go ahead and rewrite this over here. So x is equal to the square root of 100 over 3, and the square root of 100 of course is 10, and once again we can rationalize this denominator, so we end up with 10 square roots of 3 over 3. And just to give us an idea, this is approximately here like 5.77, not 75 but 77. Now we have our x, we go back up, and I think in the real world we'd be rounding this stuff off, but we want to find our h, and so we would take our 5.77 and plug it into h up here and get our h, and it seems like it's like almost 5.78 or so. Alright, moving through optimization problems. This one here is what we're going to do is we're going to set it up and then graph it and maybe try to get an approximation to this thing. Okay. Anyway, we want to find the minimum distance from a point on the curve, and this is going to be our curve x squared to a point in the plane, and that point is going to be on the x-axis 2, 0. So let's actually look at a picture. Alright, we have a point here in the plane, and that point is 2, 0, and then we have our curve, which is x squared. So we want to find the point on the curve such that if we were to find the distance between, let's say, this point here and 2, the distance, okay, we're looking at the distance between the point on the curve and 2, 0 here, and that distance is a minimum. So as you can see here, okay, if we were to look at the distance between 1, 1 and 2, 0, we could see that that distance is less than, we'll look at an extreme case here, that distance is less than, for example, up here at, trying to round off some numbers here, 2, 4, right? So the distance between 2, 4 and 2, 0 is obviously greater than the distance between 1, 1 and 2, 0. And of course, if you were to look at the distance between 0, 0 and 2, 0, you know that that's going to be greater. So we know that that distance is going to be, it looks to me like it's somewhere right in this area. Okay. All right, well, let's set the problem up. All right. So we have the point in the plane, and that point is 2, 0, and then we have our curve, which we'll just say it's y is equal to x squared. But more generally, if we were looking at a point on this curve right here, it's going to be x, and then our y value is x squared, right? So in our ordered pair, this is our x and this is our y. Okay, but instead of writing y here, y is equal to x squared. So we're going to use the distance formula. And just real quick here on the distance formula, remember what the distance formula is. It's the distance is equal to the square root. It's the change in x's plus the change in y's, and the difference in x's and difference in y's. So for example, we'd have 2 minus x squared plus 0 minus x squared, and that whole thing is squared. So this is the guy that we want to actually graph and take a look at what the minimum is on the graph and just get an approximation. And I think that's what we're going to do. I don't know, I may work through some calculus here. We're going to try to simplify this down a little bit. We have 2 minus x quantity squared plus, we've got square, so that's x to the 4th there. Yeah, let's just go ahead and graph this, and then let's look at the graph. I have left our original curve here on the screen. Well, now remember, we're just concerned with the x, and remember what the y here represents, this 1.358. It represents the actual distance, alright? But the 0.835 is the number that we're actually looking for, and therefore if we went straight down, we're looking at 0.8, what was it, 0.83 something? Okay, so that looks about right? The distance between our cursor here and the blue dot is a minimum, right? So there it is. At the bottom is the minimum, and you know, we're pretty much done, because all you have to do now is take that 0.835 if we want to find what the y value is, right? What the y value is, of course, let's see. Alright, I've kind of forgotten, this video was recorded earlier, and I've kind of forgotten where the heck I'm at here. But anyway, we found the minimum distance, which was 0.835, I believe. I think we already talked about that. And we want to take that and find our y value. So we would take that 0.835 and plug that in, and let's go to that. Right. So to get our y value, we would say y is equal to 0.835 quantity squared. And that should be equal to the number that we were just displayed for that other part of the ordered pair, the y value. Now let's just go back and look at the algebraic part of this calculus. Remember, we take the derivative, we set it equal to 0, and then we solve for our variable x, for example, here. And I'm just going to kind of run through that. First off, I'm going to rewrite this, and this is all raised to the half power. So we want to get it out of radical form and get it into exponential form. Now we want to take the derivative. I say d prime, bring the half out front. We have 2 minus x quantity squared plus x to the fourth, and we subtract 1 from the exponent, and that gives us a negative half. Then we take the derivative of the inside and bring it out. So the derivative of 2 minus x raised to the second power, we bring the 2 out front, rewrite what's in parentheses, subtracting 1 from the exponent, and then taking the derivative again of what's in parentheses here, and that's just going to be left with a negative 1. And then of course the derivative of x to the fourth is 4x cubed. And there you go. What you'd want to do is take this down into the denominator because it's a negative a half, and then we would be left with this stuff up in the numerator. And remember, you're setting it all equal to 0. So what's going to end up happening here is, of course, this half is not going to matter. All right, and it's really just the stuff up here in the numerator that's going to count. And I'm going to rewrite this as 4x cubed plus, let's see, that's 4, that's a negative 4, positive 2x, okay, plus 2x minus 4. Good luck trying to factor this. So you type this into some algebraic system here and find where it crosses the x-axis. Okay, graph this, find where it crosses the x-axis, and you can kind of approximate that by looking at that, and that's going to be your x, and that should be the 0.835. Okay, you can write a computer program in Python. I'm hoping to upload some tutorials on actually approximating this stuff using Python at some point in time in my day. But that's a story for another time, I suppose. Anyway, where are we at? Yeah, if you hadn't done any programming, I highly suggest get started with Python. It's a great language. You can do some great stuff with it. They've built a lot of different libraries. Do good stuff. Alright, we're moving back on. So anyway, the whole idea here was we've forgotten our calculus, or actually we got things that are extremely hard to factor and so forth. We need to have some algebraic systems for approximation. But you know, the big deal is set it up, graph it, and you know, just get an approximation. We'll be good to go, right? Okay. I guess that ends this problem. Alright. Alright, we are working optimization problems. And in this particular problem here, I'm not going to actually state it in words. I've got a nice little picture drawn for you. So what we're going to do is we're going to draw a line through the x and the y axis here, or x and y axis, and we're going to inscribe a rectangle inside the line such that this corner right here has a point in common with the line. Alright, so as you can see, A is what we're looking for. I'm calling A on the x-axis, and then the point is AF of A, and this line will be defined as F of A. So we got a nice picture to look at. And of course the idea here is we want to find the rectangle that we can inscribe in here such that it gives us a maximum area. It gives us a maximum area. So if you can imagine the rectangle being drawn here, right, it's going to be a much smaller area Then of course the one seen here, now I just kind of guessed at what it might look like. But anyway, so let me go to the drawing board and let's sketch out some pictures. Of course, they're not going to be as nice as this. Alright, so here's the idea. We are going to be given, try to sketch out, do some sketching here, use a different color, of course. I think I used red as my line. Right, so we got a line that's passing through here like this, and we want to, I'll make this box inscribed here, and what we want to do is find the rectangle that has the maximum area. Right, so there's a point right here on the line, and of course we call this A, and then this point right here we're calling A F of A. Okay, well, of course this is a more general description, but the actual numbers here, the line is passing through the y-axis where y is 4, and through the x-axis where x is 5. Right? And so therefore we'll call it f of x is equal to, we've got the function here that's going to describe this line, is negative 4/5 x plus 4. So surely you know how to come up with this, right? Find the slope, and then the intercept is y-intercept is 4 here. Alright, so now what we're going to want to do is we need to set up our primary equation. So this is our secondary equation. We want to set up our, this is the equation to our line, is what I meant. And what we're going to want to do here is set up a primary equation that describes the area of this rectangle. So the area is equal to, okay, so this is going to be, right, it's length times width, but we'll call this piece right here the I don't know the length, it doesn't matter, but anyway, this distance is going to be A, and then of course this distance here will be F of A. So A times F of A. So our F is up here, our F of X, and we're just going to plug A in for X here. So this becomes negative 4/5 A plus 4. And that's our area. And of course this is what we want to maximize. So now what we're going to want to do is take the derivative of this, set it equal to 0, and solve for x. So we've got our primary equation set up. Everything's in terms of a, so we want to go ahead and take the derivative, set it equal to 0, and solve for a. But before we do that, I'm going to distribute this a across, so this becomes negative 4/5 a squared plus 4a, and we'll just label that as a for area. Whoops, my workspace has gotten kind of cluttered over there. Okay, scrolling on down. So we want to take the derivative of this. We'll bring the 2 out front, and 2 times 4 is going to be 8. So we have negative 8/5 a plus, and the derivative of 4a is just 4. And that is our derivative. We set it equal now to 0, and we solve for a. I left off my a right here, and there was something else I noticed. So math is all about pay attention to detail, isn't it? Alright, so negative 8, or actually positive 8/5 a is equal to 4. And we multiply both sides by 5/8. So a is equal to 4 times 5/8. And then we can simplify this down even more. A is equal to, so let's see, 4 goes into 8 2 times, and we are left with 5/2. We're left with 5/2, so that goes into, let's see, 2 point something times. So A is equal to 5/2. Alright. And so to find what this other point is, you're going to take the 5/2 and plug it back in, right, to the equation for our line up here. And I'll just do that right here. So we're plugging in 5/2, right? So this to find the other part of this ordered pair is equal to negative 4/5 times 5/2. Hey, that's nice. 5's cancel out. 2 goes into 4 2 times. So we have negative 2 plus 4, and that just gives us a 2 there. Alright, a 2. So our actual ordered pair up here, we'll have to write it down here. So the point on that line, 5/2 and 2, that's going to be the actual point on the line. And if we wanted to find the actual area of the area of the box, you would take the 5/2 and the 2 and plug it into either one of these right here. That gives us the actual area. But I think what I'm going to do here real quick is I'm just going to graph this. So let's graph this and see if we come up with these same numbers. Hopefully we do. Alright, so we graphed the equation for our area, which was negative 4/5 x, or was it a squared plus 4a. Anyway, as you can see up here, when we graph this now, this graph, the x represents the a, of course, and then the y-axis represents the area. And as you can see, we have a maximum up here at the top, and of course at 2.5, and then the 5 is represents the area in this ordered pair here. So you have a maximum area of 5 and 2.5, and then we just take the 2.5, of course, and plug it in to find out what the second part of that ordered pair was. So it's always nice to graph this stuff. You can check your work or skip the calculus and just graph